Hello, I'm Ethan J. Armis, and this is the Physics 2211 Lab 5 report. This lab was constructed for the purpose of observing the peculiar motion of a spring in freefall, a slinky in freefall, modeling it with known formulas to predict its behavior. The important physics principles that we're going to use is Newton's second law, the momentum principle, which can be rewritten as the velocity update formula. We're also using the position update formula, the formula for quadratic drag, where it is relative to the square of the velocity, and the force of gravity, which is just mg. In this system, in this experiment, the system was the slinky, and the surroundings were the earth and air. The bottom of the spring is tracked, and it is initially at a resting condition. The top is then released in a free fall with a non-zero velocity downwards. What is observed is the motion of the bottom of the spring. At the end of the experiment, and after creating a computational model, comparing the two data points, we can see that once the top of the spring is released in a free fall, the bottom of the spring doesn't begin to fall until the entire slinky is fully compressed. Here on the left is a comparison between the computational model and the actual data. The blue is the actual data, and though the data points are, the model is a little bit slower and falling, the general motion is exactly the same. The bottom of the spring stays completely still until it reaches a certain point once the slinky is compressed, and then the entire slinky falls. As to the possible sources of error as to why the model is slightly different, I believe it's because I had an inaccurate drag constant, and I also had an inaccurate drop time reference point, meaning given the frames of the video, I think it started dropping a little bit sooner than what I was able to capture in Tracker. On the right, you can see the initial conditions of the computational model, and then here you can see the two different iteration while loops. In conclusion, I believe that the spring falls with this peculiar motion because the bottom of it staying in the same location, well, the peculiar motion is that the bottom of it stays in the same location once it begins to fall. I believe it is because that as it is falling, both ends are being compressed together towards the center of mass. An expanded spring wants to come back to equilibrium. But the center of mass is also falling, which is the middle point between the two ends. And it is falling at the same rate as the bottom of the spring is being pulled up. That can be explained here as the force of gravity is equal to the upwards force of the tension of the slinky. Since it's being pulled at the same rate, the bottom of the spring has no vertical motion until the slinky is fully compressed, and then it begins to fall with the center of mass. This lab demonstrates that we're able to use simple physics principles to not only predict certain strange phenomena, but also explain them. And yeah, thank you very much. Oh, and also, there was no what if or what does it mean for this lab, because Lab 5 is a choose your own adventure, so nothing to explain there. But yeah.